we go. Okay, well, welcome to January's TDSL seminar. And so we've been talking a lot, I think, in a lot of like our recent similar seminars, we've been talking a lot about advanced analytics, including a lot of stuff about LLMs and geospatial work, as well as recently sort of looking to the future of AI and AI platforms. And so we wanted to take this month to visit a topic that has been discussed very briefly in a couple of our seminars, but wanted to take a deeper dive into, I think, what is now really being referred to as classical machine learning. And so to put this into context real quick, I think this is a diagram that we've showed variations of before, but just to sort of situate where we're going to be today. Right. So when people refer to artificial intelligence, we're generally thinking of that as like a pretty large umbrella term, as generally referring to any sort of technique where a machine tries to mimic human behavior. Machine learning is generally considered sort of a subset of all artificial intelligence, and I think you could basically like talk about or like a one sentence description of machine learning as machines just trying to learn patterns and using, in some cases, statistical methods. There's lots of variety in there. Within that is where deep learning sits. And that's when, if you're talking about generative AI or large language models or the neural networks, those all fall within deep learning. And so today, what we're going to be talking about is the subset of machine learning that is not inside of deep learning. And so is sort of this outside part of this diagram. And I would say just for like a little bit, one more slide of context before we get into things. I think that like machine learning and all of its parts have a much longer history than I think most of us have really than has really like really been in the public conscience. And so here is a very abbreviated and very nonlinear history of machine learning. And I'm not going to go through all of these, but the point here is that pieces of machine learning, especially a lot of theory that was developed in the second half of the 20th century. There's sort of foundational principles that go back centuries before then. But you know, I think in a large way, I think sort of machine learning has really become like more popular, say maybe within the last 20-ish years, really as I think computationally we've been able to do a lot more, and data sets have increased in those sorts of things. But when we think about building machine learning models, and particularly in a clinical context, I think there's like three primary pieces of like what actually goes into making a successful machine learning model. And this is basically the outline of what we're going to talk about today. So we're going to start by talking about the quality of data, talking about making sure that it's clean and relevant and accurate. We'll spend some time after that talking about model choice, and some ideas that you can think of when you're considering all the options, in particular thinking about what are the outcomes that you want. And then we'll also talk about sort of the last step here, which is choosing a metric that actually makes sense for your particular project and the outcomes that you're going to look for at the end. Okay, so let's go ahead and jump into this first part, which is data quality. And so there's again lots of pieces here. I think we'll just sort of start with the very first and most basic step, which is generally referred to as data cleaning. This is sort of an umbrella term that I think people could refer to like all of these next set of slides that I'm talking about as data cleaning. I'm going to sort of like separate it out here just for a moment. But I think we really want to think of data cleaning as like data that's preparing the data for the analysis. So this is how we interact with the data before we send it to the model, right? So the model hasn't touched it yet. We're just making sure that like what we have is what we think we have and what we actually want to have. And I think this is particularly important for EHR data, because I'd say all data is messy, but EHR data in particular is very messy. And so, right, we can think about, you know, if for your outcome of interest, right? Different people in your cohorts are going to have different amounts of data. That's just sort of the nature of working with EHR data. But this is also very different than working with clinical data or like clinical trial data, I guess, like where that tends to be like very regimented. And so you like people are coming in for at the same intervals and getting the same labs done and those sorts of things. Another common thing you have to sort of be aware of for like data in EHR is that different labs have different units. So you actually want to make sure all your data is standardized. I think another sort of common example of EHR data being messy are diagnoses. Right, and so oftentimes diagnoses can be used to justify testing for something, but that doesn't mean that person actually has that. And I think a common example here is cancer, where there's a paper from a couple years ago that like calculated that like roughly like 50% of people who have ICD-10 codes for cancer don't actually have cancer. That's like in their chart because they were suspected of having cancer, and so they needed further testing. And so there's a few other pieces here that you have to think about, right? So missing values sort of refers to like people having different amounts of data. You have to think about outliers. So as you go through each of your variables or features of interest, you're going to have outliers. Whether or not you do something with those is going to sort of be a consideration that you're going to have to think about. And duplication, right? You don't want to have multiple rows, for example, that have the same patient with like the exact same information. That can skew your data in a couple of different ways. Um, so after you get the data cleaned up, you're like, at least how I tend to sort of think about this process is you clean it up and then you are really working on like the packaging it for the model. And there's a number of steps here in terms of packaging data for the model. But I think I'll start with the most simple, which is often referred to as feature selection. And so throughout this presentation, I'm going to use the word feature a lot. Feature is just another word for variable. So you can think of, right, whether this is a diagnosis code or a lab result or a procedure code, right? That's just the same thing as a feature. And here really the idea is that not all variables, not all features are going to be particularly useful. And so just because you can include it in your model doesn't necessarily mean that you want to. And so you want to think about really what is clinically meaningful, right? And so I think an example I thought of here is just because somebody had a procedure from 5 years ago doesn't really, if they're presenting to the ER, that doesn't necessarily going to, tell you anything about their readmission risk for something that's completely unrelated. And so you would sort of want to go through that. There's in the EHR data, there's a lot of stuff that you can get, but you don't want to take all of it because that can sort of overwhelm your model. We'll talk a little bit more about that later. But just because you can include things doesn't mean you actually want to. So feature selection is identifying which ones to use. There are a number of approaches here. I'm just sort of throwing these out so that you have a place that you can go look and refer to, and as you sort of come across this step in your machine learning pipelines. But a number of approaches here to deciding which features are most relevant. You can do a variance threshold. You can select a certain number best, or you can do it in a percentage wise. You can do recursive feature elimination, which is sort of this process where you go through and sort of remove one or a handful of features at a time and sort of see what your model looks like afterwards. Another common data preparation process related to feature selection is called feature engineering. And so this is when you take individual pieces of information and you combine them to make them more powerful. There's a few examples up here, right? So you can combine height and weight to get a BMI. You could combine weight and age to get an expected dosing. The others are shown here. But the idea is that like models don't necessarily learn the best from raw data. And so we want to supply the models with like the most clinically meaningful data set that we can. And so this is where like feature engineering can be like really powerful. And so there's an example here on the right of a paper from a few years ago now. That I think is a really good example of this, where instead of providing their model with these 4 different, like very specific prescriptions that patients could get, they combine these, they basically group these into like what the like actual drug ingredients are, right? And so I think this is a good example because for most of the time, I think this is probably true, right? You don't really care whether someone is on like a 20 milligram oral solution or whether they're on some sort of extended release tablet, like unless that's like your outcome of interest, right? But you do care that they were on that particular drug. And so I think this is a good example of how we can combine information so that we have less info or we have fewer pieces of information, but pieces that are more powerful and more helpful for our models actually learning what we want them to learn about. So we're going to take a slight step in a slightly different direction here, but still thinking about packaging data for our models. There's really, I'd say data comes in sort of two forms or fashions. And this is what we refer to as continuous data or categorical data. And so we're gonna go through both of these and talk about what these are, talk about some examples, talk about how we deal with them for classical machine learning models. But I think one important piece to keep in mind here is that like how we deal with these is really indicative of how our computers can understand them and process the data that we give them. And like sort of the subset of that is that computers really need numerical data to apply the algorithms. We can't just give them text. And so their computers are trying to understand the numbers that we give them. And so we have to be careful with the numbers that we give them. I think continuous data tends to be a little bit easier to work with, so we'll start with that. So continuous data, numerical data where both the value and the distance between the values are meaningful. So there's lots of examples of this. So age, weight, BMI, lots of lab values, right? So HbA1c, creatinine, sodium levels, vital signs, right? Heart rate, oxygen saturation. I think these are all like really good common examples of continuous data. And so continuous data, a lot of people think that it is easier to work with. One thing that you have to be a little bit aware of when working with continuous data is that the scale matters. And so you don't typically want to just take the raw numbers that you're actually given them. And so you need to scale them. And this is really a mathematical issue for like how the models are going to process them, not a clinical one. And so I gave an example here, right? So if you take an age, right? So age, let's say it can range from 0 to 100. If you wanted to compare that to creatinine levels, those are typically between somewhere, depending on the units that you're using, of 0.5 to 1.5. And so if we have a patient or actually if a computer is trying to compare a patient who is 50 or 60, that feels like a relatively large numerical difference compared to a creatinine level difference of like 1.5 to 0.5. But I would say most clinicians probably think that patients who are 50 and who are 60 are much closer, like, or much more similar to each other than a patient who has a creatinine level that are sort of at these extremes. And so this is why we have to think about the scale of the values that we are doing. And so typically as part of packaging your data for these machine learning models, when you have continuous data, you're going to want to normalize the data. And so normalization just refers to basically putting the numbers on a standard scale. And because again, like differences in range and units are just really hard for computers to differentiate. It can lead them in the wrong directions. So I think this is from a paper. It was a proteinomics paper, but I thought that gave a good visual example of it. Where on the left here, these are a whole bunch of different variables, a whole bunch of different features, and you can see so the raw numbers, right, have mean values that are very different. They have very different ranges, right? Some you can't see on here, some take up most of the example range. After normalization, right, the means are much more similar to each other, not exactly the same, but much more similar to each other. The ranges are sort of all on the same-ish scale. And so doing this normalization process is going to allow the models to understand the differences between the numerical differences within the particular features in a much better way. And so this really helps models to converge more quickly, to get to an answer more quickly. It helps us to get better predictions. It helps the models to learn the appropriate weights a lot better. Similar to like feature selection, there's a number of different ways to normalize. I've listed a few of those here. And like I think there's not a like a single answer in terms of how you should normalize your data. I think it's one of those things where in some cases you can sort of try different things, see what that looks like in terms of your results. You have to think about sort of what the data is, what you want it to look like afterwards. And so there's a number of different considerations you can think of as you think about normalization. Okay, so that is continuous data. So I'm going to move on now to categorical data. So categorical data just refers to when we have data that is in groups or categories. So sex and race are very sort of easy and common examples that a lot of people think about. Right, you can think about, if you want a non-EHR example, you can think about different types of cars, those sorts of things. And so this is when we're dealing with categorical data, I think this isn't 100% true, and I'll give you an example of this, but we're often thinking of having fields that are like text related. And so this is where we have to, right, since our computers can't understand raw text when we're doing classical machine learning, perhaps that is, as an aside, perhaps that is one advantage of using LLMs, right, is that they can actually understand text. Though actually in that case, they get encoded to numbers as well. But we need to convert our text basically into numbers to have a numerical representation to help our computers understand them. And so there's two types here of ways that data can be categorical. One of those is called nominal, and one of those is called ordinal. So nominal data, we'll start here. Nominal data just refers to data when there's no inherent order to the rankings. So you can think about insurance type, right? So there's no, right, if you have Medicaid versus private versus Medicare, right? There's no a priori reason like a model should think one of those is better than another. ICD codes is another type, another good example. Blood type is as well. And so the example I have down here, right? Let's say let's say we're working on a diabetes project. We're looking at ICD codes, and so we have three patients. One has an ICD code of E11, and then two of them have ICD codes of E10, right? And so we need to convert those to numbers somehow. And so there's three different approaches I've listed here. One's called one-hot encoding, label encoding, and binary encoding. The example, what I typically do is I typically use one-hot encoding. I think that's probably sort of like the general recommendation. And so that's the example that I'm giving here. So in one-hot encoding, what we're doing is we're taking each of the unique labels that's in our column of interest, and we're turning that into an individual column that tells us 1 if that value is present, or 0 if that value is not present. And so so basically for one-hot encoding, instead of having a single column with however many unique codes that you have, you're going to have that many unique columns that are all binary 1 or 0. One thing you have to be a little bit concerned about here, and we'll talk about this in a few slides, is it's very easy for your like data to become like to generate high dimensionality where you have a whole bunch of columns. That's not necessarily a bad thing, but it is something you're going to want to be aware of. But I think this gives a good example of how we can convert sort of the idea of that, how we need to convert, in this case, ICD codes to some sort of numerical representation. The one other thing I'll just mention, label encoding is technically and formally sort of a way that you can encode nominal data. Also, most people generally recommend that you don't do this. So in label encoding, what the machine does is it goes sort of line by line. And it says, every time I find a unique value, I'm going to assign that to the next integer that I need. So in this case, our machine would go through and say, okay, I find E11, I'm going to assign that to 0. I find E10, I'm going to assign that to 1. I find, C42, I'm going to assign that to 2, and so on and so forth. The problem is when you do this, you're actually like introducing numerically, like the computers will start to think there is an order to all of these different ICD codes. And so that is something that you want to be a little bit careful with when you're doing this encoding, that you're not telling the computer that there is an order to these codes when there's not actually an order to the codes. Something to just be aware of. Okay, so let's see. Let's move on to or ordinal data, which is our other type of categorical data. This refers to just like there actually is a formal like inherent order or ranking to the data that you have. And it also means that sort of the distance between the levels is not necessarily guaranteed to be equal. And so a couple of examples here, we can think of age groups. You can think of like pain severity levels. You can think of cancer stages. Typically, the suggestion here is to do just what's called ordinal encoding, which is fairly similar to like the label encoding that I just mentioned. Where we can see in this example over here, right? So if sort of a patient's given options of poor, good, very good, or excellent, those are just encoded to numbers that correspond to 1, 2, 3, and 4. And so we're turning this into a numerical representation so that the computer can actually understand it. And this makes, in a lot of ways, I think makes sense because like there is an order, right? Like we know that excellent is better than good, right? And so having a difference numerically between those actually makes sense, both clinically and to the actual model itself. Now you do have to be a little bit careful with ordinal encoding, and there's just a couple other pitfalls that I'm going to mention here. And I'd say really for all of these, like the issue isn't actually in the numbers themselves. It's really what the model assumes that those numbers mean that you want to be a little bit careful with. So I think one potential pitfall is like automatically defaulting to ordinal encoding, and I think this cancer example I gave on the past stage is actually a good one. Right. So if you have cancer stage stored as 1, 2, 3, 4, you ordinal encode that becomes 1, 2, 3, 4, right? The models are going to assume that depending on what type of model you're going to do, that like 4 minus 3 equals 1 actually has a quantitative meaning. Right, and that might not actually like clinically make sense. It's also going to depend on what exact model you use. And so there are cases when like you have ordinal data that like one hot encoding can actually make a little bit more sense. Two other sort of like common data pitfalls or good things to be aware of are one, collapsing data too early. So an example here is like turning continuous lab values into normal or abnormal. That's going to just reduce your model flexibility. It might not be what like you actually want. And then I would say the third one is making the assumption that similar labs have the exact same units on there. And so this is an example. I was working on a project recently that was looking at GAD antibodies. There are 3 OMOP concept codes that occur most frequently in our UNC healthcare system. Those concept codes are listed here, and you can see 2 of them are on this sort of the same scale, and the other one is a very different scale. And so if you want to be careful, I think in particular with lab values, that the units are all going to be similar. Otherwise, again, you're going to just sort of throw off the model. One other piece sort of about sort of data preparation is coming back to this idea of high dimensionality data. And so like you do want to be careful, right? I think it's not necessarily bad to have high dimensional data. But there is sort of I think a turning point when like having just like thousands of columns is not actually helpful. And I think sort of like the idea here is that, right, if you're looking for similarity, say between patients, right, and that depends on 1,000 or 2,000 or even like 5,000 checkboxes, like no 2 patients are going to look alike, even if like clinically they actually are. And so this is one of those where you have to find that trade-off of how do I prepare my data so the model can understand it while like making sure that it is still clinically relevant to what I'm trying to do here. Yeah, and so I think there's a few solutions that I sort of mentioned down here and that we talked about previously, right? So you can group concepts. We gave an example of that before. And in some cases, in some cases you can consider dropping features that only occur in a small percentage of patients, right? If those are not like necessarily relevant to your particular project, you don't really need to keep them. Regularization is another sort of approach that you can include here as well. Okay, so that's a whole bunch of sort of I don't know, thoughts, ideas, concepts about preparing the data for the modeling phase. And so now we're going to turn to phase two here. We're going to start to talk about the modeling. And so in classical machine learning, there's, I would say, three to four, I think, sort of like fundamental types here. And most of all of what we're going to talk about is going to really fall under two, because I think that those are sort of the two largest ones and then the most common when dealing with EHR data. And so we're going to talk about supervised learning. And this is basically if we have a ground truth, if we know what the actual truth is, if we have what we call label data, then we're doing supervised learning. If we have unlabeled data, if we don't know exactly what sort of the ground truth is, that's called unsupervised learning. There's an in-between here called semi-supervised learning, in which like you typically have a relatively small amount of label data and you're trying to generalize from that. We're not going to really talk about that. We're also not going to really talk about reinforcement learning, which is just a little bit different as well. But regardless of like what type of learning makes sense for our project, we need to do one last thing with the data before we actually plug it into our model, which is going to be dividing the data. And the key part here, and this is really important, is that we don't want to use the same data set for like the model training and our final model evaluation. Because we want to avoid data leakage, like where we're training the model on a particular data set, but it's not actually generalizable. I think that's sort of the goal of machine learning, is to try to get a model that is very generalizable, that works on data that it hasn't seen before. And dividing the data is a really important part of this. So the general recommendation is to divide your data into three sets. One set we call the training set. This is typically the largest. This is the set of data that actually teaches the machine the actual model. Your validation set is going to be what you use to validate the model performance during the training. And then the test set is what validates your model performance after the training. So typically with the test set, you don't want to let the model see that set until like you're all done. It's like the test set is sort of like your model seeing a new patient who comes into the clinic. You want to know, how does it perform on this new patient who comes into the clinic? One last thing on the side, I would say if you are sort of looking up resources afterwards, sometimes people switch validation and test set. I don't think I think they can mean the same thing, but sometimes people like to refer to their test set as what you do during training, and the validation is what you do after training. The idea is really what is important here. But this is what the process, I think, and maybe in an somewhat idealized way, should look like. We're going to start up here in the top left, where we train our model on our training set. We're going to evaluate that model on our validation set, and then we're going to update our model. So based on our results of what the validation set looks like, we're going to update our model. We're going to sort of go through this process over and over again, however many times we want, until we sort of get a result that we're happy with. After we do that, right, we're going to sort of exit this box. We're going to pick the model that works best, that we're happiest with. And then that's at the very, very end, that's when we're going to sort of finally confirm our results on our test set. That, again, that's sort of the set of data that that the model has not actually seen before, that sort of helps us to understand how generalizable are our results. There's really, when you think about sort of dividing up your data here, there's really no magic percentages. I think these are probably like sort of the most common three that you see, right? Having your training data at 60, 70, or 80% are the most common. A lot of it sort of depends on the total size of the data that you have. I think sort of understanding what your outcomes look like within that data is really important. I think you have to remember, right, every additional data point that you train the model with is like one less data point that you can test or validate the model with. And so it's just sort of a trade-off here in terms of what makes sense. When you're splitting your data, you also want to think about, do you just want to do that randomly, or do you want to stratify it by the outcomes of interest? I'd say for probably most EHR applications, it makes sense to do stratified sampling. It's probably not 100% accurate, but I think most of the time that is going to be what makes sense. Another approach that is commonly used here when we think about sort of splitting up the data is doing what's called cross-validation. This is something that's very helpful, and I do this pretty much all the time. So cross-validation allows the model to see different combinations of data before producing sort of an average result at the end. This is really helpful in particular to help make sure that the model is not overfitting, which is something we'll talk about in a couple of slides, but basically means that like the model can't generalize. And so what we do in cross-validation here, right? So we take our full training set. This is what's called, the example that's given here is what's called five-fold cross-validation. Sometimes you'll see people talk about 10-fold cross-validation. Again, this is one of those things that just sort of depends on your particular preferences and how much data that you have. But with cross-validation, so we go through these iterations, right? In this case, 5 times. We're going to break the data set into 5 different pieces, or we're going to break our training data into 5 different pieces. Each of these times, we're selecting, right, a different subset of that data, both for training and then for our validation. Right? And so you can see, like fairly simply here visually, how the data that goes into the model to train it in every iteration looks a little bit different. Our validation data also looks different. And so this helps us to find a model that does a better job of sort of I think that is more generalizable and can like really mimic more real life situations. Okay, so now that we've prepared the data and split it, we're ready to train our model. But before we do that, we have to actually decide what model we want to use first. And so I had said we are going to talk about these 2 different types of learning. So the first one is called supervised learning. I think this is going to be like the more common example of what people using EHR data are going to typically use. And the idea with supervised learning is that we know what the outcome is going to be. We have like a ground truth. And so each training example that I have has like a known outcome. This is sometimes referred to as the label. And so the model is going to learn what patterns are going to best predict that outcome. And it's also relatively easy to measure the performance in terms of whatever favorite metric, right? Sensitivity, specificity, positive predictive value, accuracy, recall. You take your pick. I think one particular important like point if you're working on a supervised learning project or you think you can is that you want to think about how you can actually determine what your ground truth is going to be because that one, it has to be accurate, and 2, that is not necessarily something that can always come from like directly from the EHR, depending on exactly what you're interested in. And so, right, sometimes this is going to, right, you need to do chart review to understand like which of your cases are actually like your outcome of interest, which are like not your outcome of interest. So you can have positive and negative examples. A couple of sort of like specific examples in terms of like supervised learning applications would be like predicting 30-day readmission to the ED, thinking about mortality risk or disease classification. There's a number of models like that fall within supervised learning. I've listed a couple of those over on the right here. I'm not going to get into exactly what those are, sort of the distinguishing features of each of them, but there's a number of models that you can consider using here. Okay, so that's supervised learning. For unsupervised learning, this is when we don't have a ground truth label, right? So there's no outcome variable provided. Instead, what we're looking for, or you can often think of it as clustering, we're looking for similarities or sort of patterns between the data. This is sort of slightly more often used for like sort of initial exploration or hypothesis generation. There's a sort of example over the right where sort of we're looking for clusters of data. Um, these models typically sort of fall into two stages, either like generally referred to as clustering or dimensionality reduction. A couple of examples here, like relevant to EHR, would be like patient phenotyping or discovering utilization patterns in sort of EHR encounters. Um, and sometimes you can also use unsupervised learning as like actually like a feature engineering step. And so this is, I think, particularly used for like maybe like when you have that like really high dimensionality data, and you're trying to reduce it to right from thousands of columns to, I don't know, a more manageable number. You could do some unsupervised learning to see if right your features fall into noticeable or distinguishable clusters. That then you can use that to actually to feed on to your next model. So you can use unsupervised learning as feature engineering occasionally too. Last little bit almost on models is are what are called ensemble models. And so I think this is another one of those things that I think most of the time, like I think most of us in TDSL are going to suggest doing some sort of ensemble model. And so ensemble models are basically when you're running multiple models that are going to combine at the end. And the idea is that these are going to reduce variance and instability. They're going to help you improve like the generalization performance. They're going to help you improve overfitting. And so it's a way to get multiple models to look at your data to produce the best result at the end. These typically fall into like these three strategies. First, which is called bagging, which is when we're training the models independently on resampled data. The most common example of this is a random forest, where instead of having like a single decision tree, we can have a whole bunch of, we can have 500, 1,000 decision trees. Those results are then sort of combined together at the end to give you a single result. Boosting is another type that's a little bit sort of more focused on like what the errors in the data look like. The most common example here is a technique called gradient boosting. Stacking is probably like the least common one in which you're like actually using we're using different models to create like a meta model at the end. So you could combine like a logistic regression with a decision tree with a neural network. Again, I think that's probably like the least common, but is technically an ensemble method and is a possibility. One additional consideration here as you work on choosing a model is returning really to like what your data looks like. And this is important, I think, in particular for EHR data because your data is often imbalanced, which means that like your outcome of interest is not going to be roughly 50% of like your negative outcomes. For example, let's consider a disease that affects 1% of people. Right, if our model predicts that nobody has the disease, right, our accuracy is going to be 99%. And so like while that accuracy sounds nice, this model is useless in terms of actually finding the people who have the disease. And so right, in this case, we have a very imbalanced data set. Most of our examples are negative. And so there are a few sort of approaches to dealing with imbalanced data that I list here. So you can resample, which is when you're going to sort of oversample the minority class, or you can also undersample the majority class. Both of those have I think maybe considerations, things that you want to be a little bit careful with. All right, oversampling can easily lead to overfitting. Undersampling means you can discard useful information. So you just sort of have to be a little bit careful with that. Ensemble methods tend to be a little bit more robust with imbalanced data sets as well. You can adjust the weights, which tells the models to pay attention to like the minority class a little bit more. Thinking about appropriate evaluation metrics, which we'll talk about more here in just a couple of slides. And then also generating synthetic data is another example as well. So we can use basically what we already have and generate other synthetic examples that are not exactly the same, but are at least intended to represent what our actual data looks like. And so once we choose a model, I think I would say like the biggest risk isn't really choosing like the wrong algorithm. It's when we is being careful that we don't fit the data too well or too poorly. And so this is what we call underfitting or overfitting. And so you can see in the example here, right, underfitting, right, means our model is too simple to explain the variance. Overfitting means that, right, it's basically we're force fitting it, so it's too good to be true, right? And I think when we overfit things, right, this is often when we think about having models that are not generalizable to sort of new results that they see, right? We want to find that balance of not doing either of those, but finding something that that actually fits the data appropriately. And so I think really sort of one of the the main ways that we can pay attention to these and make sure that like we're finding like the correct amount of fitting is thinking about our evaluation metrics. And so different metrics are going to answer different questions. And so this is where it sort of comes back in a lot of ways to like the project overview or the project description, where you want to think very carefully about what like your outcome of interest actually is, because a model can look very good by one metric and fail clinically by a very different metric. And so, right, oftentimes we don't want to think about like a single number by itself. Usually a couple of numbers can help us understand to make sure that the results that we get actually like make sense. So I gave a couple of examples over here about like sort of maybe some of like the more common metrics, right? And so depending on what exactly like we're looking for and what our data has, right, can influence what metric that we actually want to use to evaluate our particular model. And so a couple of like questions or ideas that I think I often sort of refer to when thinking about metrics are these, right? And so like, what is the cost of false negatives? What's the cost of false positives, right? How common is the outcome? That's getting back to how balanced our data sets are. And this last one, which I think is important, but maybe is more important if you're thinking about like operationalization, is right. Is this model going to trigger an action? Right. And that's, then you want to think about, okay, how are people going to interact with the results of this? What is that going to mean in terms of, right, avoiding decision fatigue, alert fatigue, and those sorts of things. And so you want to really like find the balance of right the metric that is like makes the most sense is going to depend on your clinical goals and your risks and your prevalence, and you want to make sure that like the models actually reflect I would say like clinical decisions, not just statistical performance. Okay, let's see. Wrapping up here, there's I wanted to sort of like try to give like a couple of concrete examples of like, okay, if I am programming these things, like where do I even start? And so there are, for both Python and R, there are a whole bunch of packages out there that you can find that cover the whole range of classical machine learning. I think um, these are good starting points. Maybe I'll sort of start there. I think in Python in particular, I think scikit-learn has like a whole bunch of basically like the pre-processing steps and data encoding steps that you'll need. If you're using Python for classical machine learning, scikit-learn is going to be probably what you use most often. But again, there's a wide variety of options out there, and sort of turning to Google and looking around is sort of like a good place to go. But if you're sort of just getting into this, hopefully this is at least a starting point of a couple of packages to look up, both in Python and in R. So I will wrap it up here, and we can have some questions and discussion for a bit. I'll just remind you that you can find all the recordings of our seminars and register for future seminars at this link. The next month's seminar, JP Powers is going to be talking about limitations and pitfalls around using both machine learning and large language models in research. So I will end there. Thank you.
I have a question while we're reading.
Yes.
Can you say any more about what you mean when you were talking about using ensemble methods as a solution for imbalanced data?
The question was, can I say any more about using ensemble methods for imbalanced data? Yeah, so let me see if we can go back here. I think in some ways, actually, I'm gonna go to a different slide. I'm gonna go to this slide, which is not about ensemble methods, but I think it's sort of a similar where in some ensemble methods, right, if you're picking like different segments of the data to like give to your model, that can help. It doesn't necessarily help with the imbalance part necessarily, though you can like I think weight it that way or do your sampling that way. But I think if you're seeing different segments of right like the minority class and the majority class in each of these, because those combine in different ways, like your average result overall can your average performance overall can improve. That sort of makes sense. Yeah. Let's see, Katie, can the slides be circulated after the call? Yeah, actually the easiest, if you don't mind emailing me, I would be happy to share them with you. It's Josh_Fuchs at Madunkadoo. I'd be happy to share the slides that way. Let's see.
Slides will be in recording.
And yes, the slides will be in the recording as well. Yes. Okay, let's see. A couple other questions in the chat here. Let's see. How often have you seen neural networks used in ensemble methods? How often have I seen neural networks used in ensemble method? Probably less frequently. I definitely don't have any experience like doing that sort of example of like stacking of combining a neural network with something else. So I think that is probably a relatively rare example. Um, I would say neural networks in general are used like very frequently outside of that. I think neural networks are in particular are really helpful when you have like really large data sets that have lots of like non-linearities between them. Like those are sort of places where neural networks tend to thrive. And I mean, neural networks are basically the basis for a lot of generative AI and large language models. Like a lot of that sort of architecture is really built on those networks. Let's see. For supervised models, are you limited to binary classification? Oh, no, good question. Good point. Where is that here? Yeah. Yeah, I didn't say that. Good point. Yeah. So no, you're not limited to binary classification. So you can do either binary or like multi-class classification when you could have like multiple distinct outcomes, or you can do some sort of regression, right? So if you wanted to, predicting like 30-day readmission risks, you could do some sort of like linear regression to get a percentage. So yeah, so you can do for supervised learning, you can have multiple types of classification, or you can do regression. Good point. Yeah. Is the test data set like the same one that you use to get the outcomes? So I would say no, because really what you want to have is you want to have like your outcomes for like all of your data, if that makes sense. So the test data set is like a subset of the full data set, but I would say it includes I think this is true. Necessarily, you're going to include all of the same variables in it, but you're just sort of splitting it out. Right. So if you had, let's say you have like 5 patients who come to the ER, you're going to include all of their information, right, for all of them, the same information that you have for all of them, but you're just going to keep one of them away from the model until the very end. So you have the same type of information that goes into the model, but that one is just not seen until the end. Yes.
Piggybacking on that for training and validation, I like the slide with the splits for kind of like the 70-15-15. If you're using kind of cross validation, are you essentially using like 85 and
Yeah.
an average across multiple iterations.
Right, right, yeah. If you're often if you're so let's take this example, right? So if you decide to split your data this way, 80% training, 10% each for test and validation, but then you decide to do cross validation, yeah, you're really using 90% of your data because you're using both that training and the validation data here to actually like do the formal training on the model. Yeah, so that 90% is going to be what's split up into those 5 splits or whatever.
So is there a downside to doing the cross validation? In theory, you are training it on a larger group.
Is there a downside to doing cross-validation? I don't think.
There's a good one I know.
Yeah, okay, good. Thank you.
This is, I hear where it's advised to just do like one giant split of training and test is if your data sets are too massive, the computational power is just going to be too much for all those iterations. So that's why you don't see cross-validation as much in deep learning as you do in classical machine learning.
But even
Good
technical, just time and memory. So even with a normal size data set, it's I would say why you don't see people doing like 1,000-fold validation normally, because like you're replicating this over and over, right? Like multiples of times, and it's eating into both the processing time and the memory that you need to contain all of it.
Yeah, it's a good thanks.
Could you talk a little bit more about deep learning, sort of compare it to classical machine learning, just like at a high level?
Let's see. At a high level, can I compare deep learning to um I mean I almost want to say no because I feel like that's like a whole nother seminar of like here's an introduction to do you have something in mind?
Well, maybe so if a person is a new user, they're sort of
Yeah.
just trying to figure out like I have this predictive situation. I want to develop a model.
Yeah.
Should I be thinking about, standard things like regression, supervised machine learning regression, or trees? Or is this something where I need to think about deep learning? And how is deep learning different than those other things?
Yeah, I think so in my mind, I think yeah, I think especially if you're getting started, I think a lot of what we talked about today is probably going to be accurate. I think I'd say, I mean, I think 2 things come to mind. I think like when you might want to like 2 cases when you're gonna want and or need to turn to deep learning. One would be like if you're using images or if you're using like a large number of like notes of like free text. I think both of those are examples of when you would want to like do deep learning. And then the other one would be I think if you have like really large data sets. I think is like in like large being probably like thousands, like at least 1,000 like columns of variables of interest. I think oftentimes, or at least yeah, I think oftentimes sort of more classical like machine learning approaches can have a harder time with like really large data sets, and that's when like maybe you want to turn to a neural network to do that. Work.
I guess what is your professional perspective on, say, like auto machine learning versus manual machine learning?
I don't know if I'm familiar with auto machine learning.
Like, I mean, something like PyCarrot, where you're sort of feeding it the data and you're picking the outcome.
Yeah.
And then you're letting it do everything else in between.
Yeah, I think I tend to be a person who enjoys I find sort of black box machine learning. I have a relatively low tolerance for that, maybe. And I think this is probably particularly true with like EHR data, is that like if I like to be very careful with knowing what goes in and what comes out and having control over sort of like the different outcomes. And so I think maybe sort of an example of like when that could be helpful would be, I've played around with the data a lot. I've done a lot of different things with it. Like I really know what this data set looks like and what these outcomes look like. And so like maybe here's a time when I can sort of turn this over after am really comfortable with it.
Almost, it sounds like sort of using it for exploratory
The
data.
yeah,
analysis.
yeah, yeah. Yeah, I would say so. So tips for beginners using Python scikit-learn. Honestly, I'd say like there are like a lot of resources out there on the internet for like Python and scikit-learn and machine learning. Um, I, I was like trying to think if any come to mind, but I think honestly, if you go to Google and sort of search for Python machine learning, then like lots of different places are going to come up. Do y'all have any favorites?
I think Kaggle is actually really
Oh,
good.
Kaggle is a good one. Yeah, Kaggle.
Because it has both the data as well as the questions, as well as an interactive
It's
notebook space where you can do everything.
that's true. Yeah,
And they even have educational ones where the answers are sort of already known.
yeah,
And so you can see how your
you
performance
can
is
compare.
relative to.
Yeah,
And there's, I mean, so many hundreds of thousands of people on Kaggle that there are a million example notebooks of like, how did I approach
what does this look like?
kind
Yeah,
of stuff. Yeah.
that's a good. Yeah, I had sort of forgot about that. Yeah.
Yeah. Um, one that I think is very valuable. There's a course that is free online, and it's from actual developers of scikit-learn. So that's how I learned to use it with Python. I thought it was a good course. It's available on fun.mooc, which is the France Université Numérique. So,
Okay.
of course, it's still in English, though. It's still available.
Yeah, it's still in English. Okay.
But
Okay.
yeah, so it's from the actual developers, so they go backwards.
Okay. Nice. I haven't heard of that one either.
It can be hard because there's almost
That is true. There are almost too many resources. Yeah. Yeah. Yeah.
Do you have any particular thoughts or perspective on classical machine learning in R versus Python? Someone
I
is trying to make that decision.
I do not. Yeah. So R versus Python. I mean, I think I would probably refer you back to our R versus Python seminar that somebody gave at some point. JP gave maybe a while ago. Um, yeah. I mean, I think I don't initially think one is better than the other. I think I've always used Python. Other people use R. Yeah. Um. Yeah, so I mean, so I'm working on a like a renal colic project looking at people who have renal colic and show up in the ED, like what is their sort of fundamentally like what are risk factors for readmission within 30 days. And so, right. So that's what that one's like. So we can use supervised learning, right? Because we know at least from like at like UNC Health, right, if those people come back within 30 days, and so you can look at their care like during their initial ED visit to see, what are the things that are going to indicate whether or not these people have to come back to the ED within 30 days. Um, yeah, I mean, I think like machine learning versus like, I mean, traditional, I think machine learning like sort of looks maybe takes like more iterations and approaches and probably is like, can use like more computational sort of thinking, so to speak, to do that.
I mean, I feel like that's a whole other
It-
conversation.
yeah.
A lot of people are thinking that machine
It
learning just
is regression.
statistics.
Yeah.
So there's a question, is it statistics? Is it think from statistics? I would say machine learning allows you to deviate from the certain parameters that must exist for inferential statistical tests. So like, is the data hyperscedastic? Yes or no? Is it like is it a certain mathematical relationship between your variables and your outcomes? Like those things are pretty strict in like at least frequent test differential statistics. Like if you deviate those things, it's a problem for your statistical tests. Whereas those don't really exist in machine learning.
Yeah, that's true. That's a good point. Yeah. Okay. I don't see any other questions. So thanks everyone. Hope you have a good afternoon.